Hello, good day. Welcome to another edition of Today Online Class. Today, shall be discussing thermal expansion of solid. As you can see, that we have seen before that solid do expand when they are being subjected to a very high temperature. But we will see how these things are being calculated experimentally and theoretically. But before we dive into this topic, let's look at the objective of today's lesson. At the end of this lesson, you should be able to define thermal expansion and provide real-world examples. Define linear area and volume expansivity. That is, we can have expansion along the length, area, and volume as well. Then state and apply the formula for linear area and volume expansion. And also define the coefficient of linear expansion and understand its unit. Solve problem involving the expansion of solid. Explain some practical application of thermal expansivity. Now, this is introduction. What is thermal expansion? Now, look at this diagram. Look at this long pole that have red at the end. Now, where you have red indicating a small increase in the length when the ion is subjected to a very high temperature. Now, thermal expansion is the tendency of matter to change in volume in response to change in temperature. When a substance is heated, its particles move more vigorously and maintaining a greater average separation. Most material expand when heated and contract when cool. Now, look at this expansion. Now, these are typical example of particle of a solid. When they are being subjected to high temperature, they tend to move apart from each other, thereby causing a small appreciable increase of length. These are the examples of real life expansion. Now, bridge with expansion joint, railway track with expansion. Now, you must have seen this thing on bridges whereby you have small hole on the bridge. This is because the iron in the bridge also expands. So the engineer have to make allowance for the expansion of the iron or whatever material they use in constructing the bridge. Now, the same way you can see, you might have seen this gap in railway track if you live close by the railway line. These are the real example of expansion. All these things they are to make allowance for any small increase in length of the metal should there be any increase in temperature. Now, linear expansivity refers to the increase in length of a solid object when it is heated. Now, look at the first diagram. L naught means the original length. Now, when the length or the iron bar is now being subjected to a very high temperature, look at the new length. Now, to find the increase in length or the change in length, you subtract the new length from the original length. So, change in length is equals to L minus L naught. You can see there's always a change in temperature also. Now, where delta L indicate the change in length, L indicate the original length, then delta T, this sign that look like triangle, we call it delta. It's a Greek letter. Delta T means change in temperature. Then alpha is telling you the linear coefficient of thermal expansion. That is, when there is an increase along the length, we call it linear expansion. So the coefficient is called, well, the alpha is called the coefficient of linear expansivity or expansion. And this is the formula to calculate any small length, any increase in length that we have in, in the length. Once you have your change in length divided by the length equals to alpha multiplied by delta t. Now, we can also have expansion along the area. We call it area thermal expansion. Now, look at, we have a rectangular shape. We have that have length and breadth. where L naught is the original length and B naught indicate the original breadth. Now you can see there will be an increase in length along this line, then increase in breadth along this line. Now look at the increase in area that we are able to achieve when this material is subjected to it. This is the change in length times the change in breadth. When you multiply, it will give you the change in area of the this. With this one, we will be able to calculate the change in area given the linear expansivity of the material. Also, we can have the increment along volume. Now, this is the area, then along the height or the thickness, we call it increase in volume. So we can also have increase in volume as well as increase in what? Area. And this is the formula to calculate the final volume. Just like the one we have for linear expansivity, all the formula are the same. Just that we have to change length to area, then area to volume. That's what we have here. Now, these are different material with different linear expansivity. For polycarbonate, it is 70.2 times 6 power minus 6 per degree Celsius. That is the unit of. Then for aluminium, it is 22.2 times 10 power minus 6. For brass, it is 18.7. For copper, 16.6. Steel is 13.0. And cast iron is 10.4. That is what we have where we have different material. So before an engineer is building in a particular location, he have to know the temperature of that region so as to ascertain the kind of material he's going to use. Because some material expand more than the other. If you depending on the temperature though, but if you want if you want to build your project in a place whereby the temperature is low, then you have the material to use for that. Now, work example. A metal rod is 2 meter long at 20 centimeter, well, 20 degrees Celsius. That is, this is the length when the temperature is at 20 degrees. If the linear expansivity is 2 times 10 to the power minus 5 per Kelvin, we should find the length when the temperature is now 100 degrees Celsius. So we have been given the linear expansivity, that is the coefficient of linear expansivity for that material. As I've said before, all materials, they have their own linear expansivity. So how do we get the length at 100 degrees Celsius? We use our formula. We use the formula. This formula can be modified to suit whatever we need it for. If you are to find the second length, because what we are asked for is the change in length. So you can find the change in length, then you now find the new length. From here, we have the length to be 2, then the coefficient of linear specific to be 2 times 10 to the power minus 5. Then the length, which is original length is 2 meter. Then the change in temperature will be 100 degree minus 20 degree to have 80 degrees Celsius. So when you multiply, it will be 3.2 millimeter. That is 0.0032 meters. Now, when you now add it to the original length, it will give you the length at 100 degrees Celsius. You may be thinking that this increase in length is insignificant, that is not useful, that because the amount is just too small. But trust me, this 0.03032 can cause a lot of damage, can cause accident on a rail track. Should we have this kind of increment if there is no allowance for it? So this is how to calculate the new length, the length at 100 degrees Celsius. Don't forget, the question can be twisted around. It's now left for you to now modify your own formula too. Don't forget, delta L is L2 minus L1 before you can get any other parameters. Now let's look at example 2. This is an increment in volume. So calculate the new volume. The same thing say apply, just the way we saw the previous example. on linear expansivity. But the only difference here is that since we have dealing with volume and not length, you multiply the material we use in building the volume of the material is very, very important. That is the coefficient of the material we now use to get the cubic expansivity because we dealt with linear expansivity. For volume expansivity, it will be 3 times the linear expansivity. That's why we have 4.5. Definitely, linear expansivity of that material is 1.5 times 10 to the power minus 5. Multiplied by 3, it will give us 4.5 times 10 to the power 5. Now, inputting our formula, change in volume is equals to, just like we have for alpha, this one is now gamma, V naught, then change in temperature. What is changing here is just change in volume, original volume, then volume expansivity. The change in temperature still remain the same. So our change in volume will now be 4.5 centimeter squared. So our new volume will now be 1004.5 centimeter cube. Now, application of expansion. We use in to construct a thermostat. So that's why we use the metallic stripe and the stripe, a railway track expansion gaps, then bridge expansion joints, power lines sagging to accommodate contraction in cold weather. That's why you see the power line in our streets, in our area that is always sagging. So that when there is contraction, it will come back or it will reduce in size to so that it can accommodate a particular kind of construction. Those are the typical example. Although we also use expansion too to fit in rim of tires sometimes, then we also use it to refit to join two metal using refit material. Here is an assignment for you to do to work on the 3 types of expansion. I want to believe you have learned something new today. Like I always say at the end of every lesson, get a physics textbook to lay your hands on and get more knowledge on this. And most importantly, the more you solve questions, the more you think about the application in real life, the more you tend to know more about it. Till I come your way again next time, I remain my humble self, Olujimi Gabriel. Please do have a wonderful day.